Hi friends, Professor Borole is here. Now we are continuing with unit number 2, the topic MOSFET as an amplifier. Here we will see summary of notations. If you see in the table, the small case letter with the capital suffix indicates the instantaneous value or time varying value with the DC quantities. Whereas the capital letter with capital suffix normally indicates the DC value or RMS values. The small case letter like ID, D is in lowercase, like VGS, the subscript is in small case, is a time varying quantity or instantaneous AC values. Whereas the combination of capital letter and small letter indicates the phasor value or RMS value. In MOSFET amplifier, we have seen the input side voltage is VGS, that is gate to source voltage. And we know to operate the amplifier in a linear region, this linear region in MOSFET is called as saturation region. For the sake of simplicity, here onward we will call it as a linear region. The MOSFET needs to be biased in this operating region, and that can be done by maintaining the operating point values of voltages and currents. Therefore, the gate to source voltage consists of two parts. One is the DC part, that is operating point voltage, and another is the external AC signal which can be amplified by the amplifier. And therefore, VGS here shown, number 1 equation, consists of the VGSQ, that is the DC part, and the time varying part VGST as a function of time. Similarly, ID, when VGS is having DC plus AC quantity, obviously this input side DC parameter gives rise to a drain side DC current, that is IDQ, and the input AC quantity gives rise to the drain side AC current quantity, that is ID, a function of time. Similarly, the voltage VDS consists of VDSQ plus VDS, a function of time. This red color here, red color variables are the time dependent variable, and blue color variables shown in the equation 1 to 3 are the DC variables. Since MOSFET is a three terminal device, if any one of the terminal is made common between input and output circuit, then the configuration is called as common source amplifier if source is common between input and output. If drain terminal is common, then it is called as common drain amplifier, also called as CD amplifier or source follower. The third configuration is the common gate amplifier, also known as CG configuration. Now let us see the circuit diagram of a MOSFET as CS amplifier. Now we will see here the biasing or maintaining the DC operating point can be done by a VGSQ supply shown here by battery, and VDSQ on the drain side can be maintained by using the drain supply voltage VDD. Here two separate supplies are shown, one is VGSQ and VDD. Whereas in practice, single DC source can be used to generate or to get the amplifier circuit, and therefore some additional biasing components can be present in the circuit, which eliminates altogether the need of the VGSQ power supply, And this bias level VGSQ can be derived from VDD itself. And accordingly, there are various biasing schemes that we will see further. Whereas in this circuit, we will see the AC voltage Vi is added in series with VGSQ to the gate. And therefore, the voltage between gate to source is effectively due to two components. One is the DC component VGSQ and another component is Vi. Whereas Vi is the AC component and VGSQ is the DC component. Since input is AC plus DC, output will vary around the DC value VDSQ and the AC quantity can be denoted by a small case letters VDS. The total output will be VDSQ plus VDS, a time dependent function, which is shown in equation 3 above we have seen. Now, how this circuit operates? Let us suppose that the input AC voltage is applied as shown in the waveform for 1. This input voltage, if you see carefully, it will be riding over the value VGSQ because see here input is connected in series with VGSQ. So during positive upcycle, the hatch portion shown here, when time t equal to 0, when external inputs signal is 0, the drain current is IDQ. Whereas drain to source voltage is VDSQ here as shown in the waveform of VDS. Now when the positive half cycle starts here and go on increasing from 0 to pi by 2 of the input signal, the drain current or VGS is increasing, therefore ID is also increasing. The relationship we have seen, ID is equal to K into VGS minus VT square in the last lecture. So therefore, we will see when input voltage is changing, instantaneous input voltage is increasing in the positive direction, the drain current is also increased in positive direction. So therefore, during positive up cycle of the input, the drain current also completes the positive half cycle. Whereas voltage across the drain resistance RD is similar to the drain current wave shape because voltage across RD is nothing but ID into RD and shape of ID is shown in this second waveform multiplied by a constant value of RD. Therefore, shape of voltage across RD is similar to shape of ID. Now, the voltage VDS according to Kirchhoff's law is nothing but the total supply voltage VDD minus IDRD. Therefore, subtract this voltage across RD from VDD. You are getting the value of VDS that is shown here. VDS is equal to VDD minus IDRD. That waveform will be decreasing when IDRD is increasing. And therefore, the hatch portion of the waveform of VDS is shown. We will observe that the voltage VDS is 180 degree phase shifted with the input voltage and therefore between drain to source the output voltage is 180 degree phase shifted with the input voltage whereas voltage across RD is in phase with the input voltage. This way the common source amplifier provides 180 degree phase shift. Also, we have to summarize here the drain current as well as drain to source voltage is changing around the quiescent DC corresponding quiescent DC level of drain current and drain to source voltage. The operation we have seen logically same can be expressed by using graphical characteristics. Let us see the operation of the MOSFET as an amplifier. from the graphical characteristics. The first figure indicates the output characteristics and second figure indicates the input characteristics. The output characteristics are VDS versus ID. These characteristics are shown here. Then, as per the equation here, we will have VDS is equal to, from this circuit of the amplifier, VDS is equal to VDSQ plus VDS into T, and that is equal to VDD minus ID into RD. This equation gives rise to a straight line curve y is equal to mx plus c, whereas y coordinate is id and x coordinate is vds, or x variable is vds and y variable is id. So separating id on left hand side and other terms on right hand side from equation number 3, we are getting the equation like a straight line, and when you plot that on the output characteristic, we have seen this line in BJT also, and this line is called as load line. And therefore, this load line intersects the y-axis here at the value of ID is equal to ID max, and that is given by VDD by RD. And this line crosses the x-axis here at the value VDD. These two endpoints can be derived from the equation number 3. Okay. Now let us suppose that our VGSQ is shown here, the central characteristic line, and the operating point is shown here. Now when AC voltage VI is applied, the total VGS is increasing like this around VGSQ, shown here in the figure. See the arrow marker. Okay. Now when the input changes in positive half cycle, the operating point will be moving from this location towards left on the load line, and accordingly it traces the various points. Corresponding projection on id axis gives rise to the values of drain current. So we will plot the drain current. So if the VGS value changes sinusoidally, the drain current also changes sinusoidally. And corresponding drain to source voltage is changing. VDS is equal to VDD minus ID RD is changing also sinusoidally by tracing the projections of operating point Q1 here and Q2 here on x-axis and plotting the curve. You are getting the sinusoidal curve for VDS. And we see here that VDS is 180-degree phase shifted with VGS and ID. Same thing is shown from the input characteristic here. ID versus VGS curve is shown. The operating point is located here. You will see input voltage is VGS, that is varying around the value of VGSQ. When the input voltage changes, here the triangular wave is shown. The operating point is moving during, say, this positive half cycle of the input. The operating point is moving up on the characteristic curve, and therefore corresponding point on the drain axis, drain current axis, gives you the corresponding drain current. So when VGS changes here by the triangular wave shape, by the way of triangular wave shape, ID also takes the similar wave shape and it is changing around IDQ. When this ID is flowing through the external resistance RD, it produces the voltage drop across RD, which is similar to a triangular wave shape, and it generates the VDS value, that is VDD minus IDRD, which is exactly 180-degree phase shifted with the voltage across ID into, or voltage across RD, that is ID into RD, that we have seen in the waveform. The small signal components we are now observing. Up till now we have seen the operation logically, operation by the graphical way, and now we can see the same thing by the analytical model of the amplifier, that is also called as small signal model. Considering the small signal operation around the Q point, we can replace the value of VGS equal to VGSQ plus small vgs, where VGS is the signal voltage and VGSQ is the DC quiescent voltage. Therefore, it gives rise to the ID. We know the collect this drain current equation for the MOSFET. In the last lecture we have seen, refer the last lecture video. ID is equal to K into VGS minus VT square. Let us replace the value of VGS there by the summation VGSQ minus small VGS, here shown here in the equation. VGS here, the blue color is a DC quantity and red color variable is the AC quantity, minus VT. VT is the threshold voltage. Okay. So therefore by substitution we get ID is equal to K into VGS plus VGSQ minus VT square. Simplify the bracketed term. ID is equal to IDQ plus the AC quantity ID, that is K into VGS minus VT square, twice VGSQ minus VT into VGS plus VGS square. This is A plus B bracket square. You have to solve it and separate out the terms. The DC terms are separated and AC terms are separated. So here K into VGS minus VT square is a DC component. Twice K into VGSQ minus VT into the signal value VGS is a linear AC component, and K into VGS square is a AC component, but it is a harmonic term. It is a square term. In this equation, if K into VGS square is much less than this midterm, twice K into VGSQ minus VT into VGS, then we can approximately say that ID is equal to, here note the, see the nomenclature ID, the AC quantity ID is equal to twice K into VGS Q minus VT into VGS. The DC part is ignored here because we are only considering the AC part. And therefore from this equation, we can note that ID is proportional to VGS and the proportionality constant is twice K into VGSQ minus VT. Equation number 3. The equivalent circuit of the MOSFET is shown in the following figure. We know between gate and source there is an insulator, and therefore here the open circuit is shown between gate and source. Whereas between drain and source we have a current source GM into VGS. And since between drain and source there exists a channel, and channel is of semiconductor material and therefore it have a finite resistance. Therefore current source is parallel with a resistance RO. The voltage between drain and source is denoted by VDS. The gate current is denoted by IG, and which is virtually zero because there is insulation between gate and source. Whereas this resistance RO here, that can be obtained by extending the characteristic, output characteristic, to a point here on the x-axis, far remote on negative x-axis at the point VA, that is called early voltage. Because these characteristics have slope, when it extends on left hand side they come to a point, and this point is called as early voltage, and slope of this line is nothing but the output resistance. 1 by RO is equal to delta ID by delta VDS. This is all about the MOSFET as amplifier. The another application of MOSFET is MOSFET as a switch. The total digital electronics and the computer and computer related operations are based on MOSFET as a switch. And we have already discussed that MOSFETs are the basic building block or nowadays digital electronic technology. Other devices are rarely used because their sizes are larger compared to MOSFET, and therefore MOSFET suits to fabrication technology for chip manufacturing, and therefore MOSFET can be used in the digital circuit. Now, how MOSFET can be used as a switch is shown in this figure. Let us see here. Here the MOSFET is shown. Input digital voltage or on-off type of signal is applied in the form of V in here. The wave shape of V in is also shown. The drain resistance RD is connected in series with the drain and source is grounded. And output is taken between drain and source. The power supply uses VDD. Now, when the MOSFET input voltage is suddenly changed from 0 to VDD, that is input voltage V in is now VDD, get to source voltage is positive, therefore MOSFET, which is enhancement type of MOSFET, which heavily conducts because the channel is wider channel is open between drain and source, and therefore full current is flowing through this MOSFET. MOSFET is therefore virtually acts as a closed switch between drain and source. When current is flowing through this MOSFET, it produces the voltage drop across RD, and therefore the value of output voltage VOUT is given by VDD minus IDRD, whereas IDRD is approaching towards VDD, and therefore Vout is approaching towards 0. When the device is fully on, VDS is all that is equal to the output voltage V out, that is 0. So when input is fully in on state, that is VDD, output voltage is 0. It is perfectly analogous to closed switch. When input falls from VDD to 0, the get to source voltage is absent, and therefore MOSFET channel will be vanished, and therefore it acts as an open circuit because no current flows through the MOSFET. When no current flows to the MOSFET, the voltage drop across IDRD is 0, and therefore output voltage V out is equal to VDD minus IDRD is equal to VDD, and it is therefore analogous to open switch. And this way the MOSFET will be operated as open switch. The same operation, whatever I explain, is shown here in the waveform. Now let us see the P-channel MOSFET. The difference between N-channel and P-channel MOSFET is the channel nature. In N-channel MOSFET, the channel is formed by using N-type or the electron as a charge carriers. Whereas in P-channel MOSFET, the channel is formed by using P-type carrier, that is nothing but holes. Whereas since it is a P-channel MOSFET, the input voltage normally to turn on the MOSFET will be negative. Whereas in N-channel MOSFET, we have seen to turn on the MOSFET, input voltage needs or gate voltage should be more positive than source. Whereas in P-channel case, to turn on the device, the gate voltage should be negative than source. Whenever VGS is suddenly dropped to the negative voltage VDD here, the MOSFET goes in on state, and when MOSFET goes in on state, the device suddenly acts as a short circuit, and therefore output voltage will be 0. So therefore you will see here the output voltage is equal to, when V in is dropped to negative value VDD, the output voltage is reaching to 0 here, this portion. Whenever input voltage comes back to 0 volt from minus VDD, the MOSFET will be turned off and the output voltage will be same as minus VDD. The governing equation is Vout is equal to VDD minus IDRD. And when MOSFET is off, ID is 0. So therefore IDRD will be 0. And therefore Vout is equal to VDD minus 0, that is equal to minus VDD. Same is shown in the waveform. That's all, friend. This is all about the MOSFETs and MOSFET amplifier and how MOSFET can be used as a switch. So today we will stop here and we will meet in the next session in continuation, the last topic of this chapter, that is operational amplifier. Till then, bye bye.